that better? Okay, so what happened? Everything okay?
Yeah, I was looking at my notes, I'm thinking, I have a lot to do still. That's okay.
Okay, so let's try a couple of these to remember the whole strategy behind these syntheses. Okay, let's look at the first one, guys. Please tell me what's happening in step one.
Deprotonating, deprotonating the center.
Because there's only one set of alpha hydrogens, right? This
Yep.
malonic esters has only one set of alpha hydrogens, so it's creating the enolate by deprotonating one of the one of the H's from that position. Okay, what's happening in step number two?
A butyl group is added
So you're doing
in place of the proton.
nucleophilic, basically SN2 reaction, where one of the H's, therefore on the alpha carbon, is substituted by, agreed?
Yep.
What's happening in step three?
The other hydrogen is stripped off as a proton.
Good, and what about this other remaining alpha hydrogen is deprotonated and then followed by step 4, which is also an SN2 reaction. Do you agree that at the end of step 4 we will end up with this guy, pH and 1, 2, 3, 4, is that correct?
Yep, that's right.
Everybody okay? They're supposed to be connected. So what's happening in step number 5?
A equivalent of CO2 is being stripped off.
So what's the final product?
A substituted acetone.
No, not acetone, not in this case.
Substituted acetic acid.
Exactly, because there are two esters here, right? So first, of course, the acid causes the esters to be hydrolyzed. So both of the esters become carboxylic acids first. And then this carboxylic acid is a beta keto acid, so one of the, whichever one, it doesn't really matter, but one of them, it's decarboxylated, meaning carbon dioxide is eliminated out. So what's left behind as the product? So you have a substituted acetic acid. This is acetic acid, right? Agreed?
Yep.
And then one of these R's, let's say the butyl, so 1, 2, 4, 1, 2, 4, and then the other R, just to show you where all of those pieces are coming from, is the product. Does that make sense, everybody?
Mm-hmm.
Everybody okay? So please remember malonate ester, which is this guy, malonate ester will produce substituted acetic acids, alpha substituted. This portion comes from malonate ester. It's the acetoacetic ester, which is the next one, which is able to make a substituted acetone. So, what is this going to create?
A monosubstituted
The
acid.
product, please. Where is this going to deprotonate? Is that going to give us the thermodynamic enolate or the kinetic enolate? Because here there is a choice. There are two different sets of alpha hydrogens. Either the ones that are more acidic but in the center, or the ones that are less acidic but out open. So thermodynamic enolate versus kinetic enolate.
It would deprotonate at the center.
The thermodynamic enolate, because it's a weaker base.
Mm-hmm.
So weaker base, thermodynamic enolate, again, it doesn't matter which resonance structure you draw, that's not relevant, okay? And then SN2 reaction, so that will end up creating agreed?
Mm-hmm.
And then, of course, there is hydrolysis and heat. So, what's the product? And again, just to remind everybody, first the ester is being hydrolyzed to carboxylic acid. The esters are being hydrolyzed to produce a beta keto carboxylic acid, and it's the beta keto carboxylic acid that loses carbon dioxide.
Mm-hmm.
So what does that leave behind?
A substituted acetone.
Did I draw my product correctly? 1, 2, 3, 4. Make sense, everyone? Yes? Okay. If that makes sense, please go through this sequence and tell me what's the product going to be. Let's do this fast, guys. So, where is the first one? LDA. Is that creating a kinetic enolate or thermodynamic?
Kinetic enolate.
So, say that again, please.
Kinetic.
Kinetic enolate, which means it's taking one of these hydrogens only. LDA, please remember, is a bulky base. It is not good for creating a thermodynamic enolate. It's good for making a kinetic enolate, which is the less stable enolate, but taking the more accessible proton, because LDA itself is bulky. So when the first, so that's step number 1. When the first SN2 happens in step number 2, where does the electrophile go?
It goes to the carbon that's out on the outside.
Because that matters. That's where the negative is. Does everybody understand that? Is everybody okay with it? But then you're doing step number 4, 3, and 4. Now 3, where would that deprotonate? Step number 3.
That would deprotonate in the center.
Because that gives a thermodynamic enolate. That's a weak base. It does not give us a kinetic enolate, and it's not that bulky either. So that creates a thermodynamic enolate, which means that the nucleophilic carbon is the central carbon. And then we do step number 4, which means that the incoming electrophile ends up on the central carbon. Does that make sense, everybody? Yes?
Yep.
And then what's the result of steps 5 and 6? First hydrolyze the esters to carboxylic acid and then decarboxylate because it's a beta keto acid and we are heating. So beta keto acid loses CO2. So what's the product?
It would be a substituted acetone.
It would be a substituted acetone. So the product is basically going to be Did I draw this correctly, guys? Do you all agree? Now, once again, for you to see how the pieces are coming together, this portion is this piece right there. That's coming from your precursor. And then the benzyl group is coming from the first SN2 reaction, and then the butyl group is coming from the second SN2 reaction. Does that make sense?
Yes.
Everyone okay? So cool. In that case, if that makes sense, please tell me how will you use this reaction to convert A. Also tell me what should I use, malonate ester or acetoacetic ester, and how, what reagents, give me a second, 1, 2, 3, 4, 5. If I want to make 1, 2, 3, 4, 5. So the first one, which precursor should we start with? Malonate ester or acetoacetic ester?
Malonate ester.
Why do you say malonate ester?
Substituted acetic acid.
Exactly. If it's substituted acetic acid, this portion is coming from malonate ester. That piece is coming from your precursor malonate ester, ethyl diethyl malonate. The rest we have to bring in as SN2 reactions. So, first step, what do you guys think?
NaOET.
Sodium epoxide. Second step,
ethyl bromide.
okay. Next,
Another NaOET.
okay. Next,
A propyl bromide.
okay. Next, now we got the groups in there. You got this group in there, you got that group in the alpha position. You got those where you need them to be. Now you're ready to get rid of the CO2. So what do?
Atrio plus heat.
So first we hydrolyze the esters to carboxylic acid, but if you do it with heating, it also causes decarboxylation to happen at the same time. Make sense, everyone? Okay, what should be the precursor for the next one? Malonate ester or,
Acetoacetic
and
ester.
why are you saying that uses acetoacetic ester?
A substituted acetone.
Because it is a substituted acetone. So once again, please notice this whole piece is substituted acetone. You know the structure of acetone. So that's the acetone piece which is coming from the precursor. So ethyl acetoacetic ester, okay, so that's your precursor. Step number 1,
LDA.
why do we need LDA? I'm just asking, just a question.
Because
Because?
we have 3 H's
Because
and
you're
it's more.
trying to, because, sorry, but because you're trying to put,
You're trying to put it on the end carbon.
you're trying to put both of these groups on this carbon, is that right?
Yes.
Okay, cool, that's fine. LDA, and then,
Isopropyl bromide.
actually, that's not isopropyl, that's isobutyl.
Oh, isobutyl
Again,
bromide.
it's SN2, so primary substrate is the best for SN2. Okay, next,
And then do an
an Another LDA, cause you weren't on the same, oh, yeah, same position, right?
Yeah.
And then,
And then ethyl bromide,
and then,
H3O plus, and heat.
is that okay with everybody? Okay, next one. Once again, that's a ketone, not a carboxylic acid, right? So, once again, please notice, this piece is the acetone piece.
I have
Everything
a,
else we have to bring. Sorry, what?
why did we use H3O in heat when we already had that there?
What do you mean, we already?
Yeah, why, number 5?
Because at the end of step 4, after step 1 and 2 and 3 and 4, what do you have?
Oh, yeah.
Right?
Yeah.
So you need to hydrolyze the ester, that's why you need the acid, and then decarboxylate the ester.
Okay.
With
You
heat.
see that, Mark?
Yes,
Okay.
thank you.
Next one, what are we going to start with?
The acetoacetic ester again.
Because we once again have a substituted acetone. Okay? Please go ahead.
LDA.
Okay?
One, two, three.
Anybody can speak up. What do you want to use next time?
Well,
Um,
Fenner?
and ethyl bromide.
Okay? Next step.
Another LDA.
Are you sure?
No.
In this case, not.
No.
Because
Because-
you brought in this already.
And also the other group
But
is
the
on the
others
other
are
end.
on the other side.
So we would do NaOET.
Is everybody seeing this?
Yeah.
Is everybody following this? So this is where you have to switch the base because you want the other two groups on the other alpha carbon, not the same alpha carbon. So, then what? Step number 4? Come on guys, we can do this faster. This is a 2-minute thing.
Phenyl,
Not phenyl.
benzyl methyl bromide.
Benzyl methyl, what does that mean? There's no such thing.
Oh. 1 phenyl, 2 bromo.
I think you're not looking, no, let's pause. How many groups are on this carbon atom?
Oh,
That's a
2
separate
groups.
group, this is a separate group.
Okay.
These are not connected to each other in any way.
Okay.
So you can decide to bring whichever one first. So sure, we can do benzyl first and then, I'm just saving time. And again, the same base because you want it on the same carbon and then you can go ahead and bring in the methyl group.
Methyl.
They're separate. You're bringing in 3 groups here. You're bringing in ethyl, you're bringing in benzyl, you're bringing in methyl.
Okay.
And then finally, once you've got all the groups in position, now you're ready to hydrolyze and decarboxylate.
H3O plus and heat.
Does that make sense, everybody? Yes? Sure? Okay, I'm gonna write it in here for you to work at home. This is homework, please. Same kind of question is, the question is basically how? Show the synthesis. need to scroll up. That's why I need a board. I can't do this on a small screen. And got it? I need to scroll up, guys.
Mm-hmm.
Maybe we'll do a couple together, the rest you guys can do at home. Did everybody get all of them? Okay, let's do a couple of these together. How about, the last two? Let's just do the last two together. Once again, you gotta tell me what to start with and then how do you carry out the synthesis. The last. Anybody?
No,
Okay.
I did not.
First one, we start with malonate ester.
Because it's a carboxylic acid, right?
Yep.
Okay, so malonate ester, ethyl malonate, diethyl malonate, rather, I should say. Okay. And guys, please, pitch in. How?
I'm the only one who pitches it.
No, I know, exactly. But even if Carter is, we can all just together do it. How? How do we do this?
NaOET.
Okay, so you're going to deprotonate at the alpha position, NaOET, okay, then?
Bromocyclopentane?
No.
No.
So what I would recommend when you're solving or working on problems like this is chalk out, somehow delineate, somehow pick out the piece of the product that comes from the reactant. The piece of the the piece of the product that comes from the reactant is this piece. These atoms come from here. The rest we have to bring in. The rest we've got to bring in. So notice, not cyclopentane. Anybody?
Build, I don't know, hold on.
Did you guys have biology in the morning? Biology sucks out all the energy, right? And then you come to Ochem and you don't have any energy left over. I've got to talk to Ricky about this. Come on, guys.
Butanol bromide.
Butanol bromide? Are you sure? Okay, I'm gonna let you guys do this though. We can't spend time when we are just staring at each other. But you guys gotta know how to do this. These are important ones. These are important problems to actually know how to do this. Please think about it. How are you gonna create that ring and how are you gonna do this reaction? But I need feedback from you. I need your participation. Otherwise, I can just keep talking for 2 hours. That doesn't help at all. It's so boring. Okay, finish it at home, please. Make sure that you are working through each of these and know exactly how to carry out each of these syntheses. But let's go on to the next reaction, which is called. Is somebody saying something? Vincent, were you going to give me the answer to that? Oh gosh, come on. This is not fair. Okay.
Do we have to start with
Yes, Camilla, please do, and Vincent, give me a second. Camilla, no, you can, give me a second though, Camilla. Yes, Vincent, what were you saying?
Maybe beer two.
Say that again?
BR2.
BR2, what do you mean by that? Like bromine molecule? That's not, I don't think that's what you're trying to say. What are you saying, Camilla?
I was saying potential bromide.
No, no, that'll add a carbon, one more carbon, that's what Carter had said earlier also, but no, there's no cyclopentyl group that came in actually. The group that came in, the group that we are introducing is this piece, notice that's not cyclopentyl.
Okay, so that would be a butyl.
I think what Vincent is saying, even though he didn't say it, but I think what he's thinking is something different. Exactly. Exactly. This is where you have to do intramolecular reaction. This is where you have to first put in one piece in 1, 2, 3, 4, and then
Oh, a
do
dibromide.
another after that, which
Oh,
then does a. Guys, we've done this, and I need participation. It's really not going to work if
One,
you're just
two,
listening.
three.
Speak your mind. Maybe you're not going in the right direction. Okay, at least you're participating.
Pun almost had it, I think.
But you have it. You did almost have it. You just didn't put that other leaving group. But Vincent, you're absolutely. That's what you were thinking, right? When you said BR2, I knew you're not thinking BR2. You're thinking of two BRs. You just have to say it. Exactly. Exactly.
Yeah, so it would be a dibromide.
Exactly. Okay, then do you want to take a shot at the last one since you kind of sort of in that direction?
We have a substituted acetone.
Mm-hmm.
So we start with acetoacetic ester.
Okay.
ETO1. Okay. And we have a methyl group on cyclohexanone. We do an NaOET.
Okay.
We do a dibromide,
What do you mean by dibromide?
like the
Which one? Which one?
Oh,
I mean,
okay. A bromide on one of the
guys, you can help color out.
help.
Come on. We can all chime in and speak with each other and create this together. Carter is really doing well today, but go ahead.
So, is it two different groups? So, as a methyl and then.
I don't know, you tell me
Yeah.
what to do as next time.
I believe that, yeah.
What?
So, we start with a methyl BR,
Okay, you want to put the methyl in there first? Okay.
and
Then what?
NaOET.
Okay.
And
So you're
then-
deprotonating again in the central position, okay?
Then BR, CH2, CH2, CH2,
How about 1,3-dibromopropane?
Huh?
We know how to name these things. 1,3-dibromopropane, would that
Yes,
be okay?
1,3-dibromopropane.
Because you want to bring in, you're trying to bring in this piece, isn't that right?
Yes.
Made of 3 carbons, so you need a leaving group on both ends, that's 1,3-dibromopropane, okay, good, then what?
H3O plus and heat.
No, we're not there yet,
Okay,
we're not there yet.
not there yet.
Louder please, somebody said this?
Allie.
Exactly, now you're deprotonating on the other position so that this thing can go and cyclize. Do
Yep.
an intramolecular SN2 reaction, exactly, we need that. That's when the ring closed. Now you're ready to hydrolyze and decarboxylate. Does everybody understand that? Does
Okay.
everybody understand what's going on each step? Yes, Mark?
No, I'm trying to
Oh,
figure it
okay.
out.
Yeah, I mean, that's the important part, is strategizing. So, if you do steps 1 and
That's a
2,
mouthful.
1 and then 2, is it going to the kinetic side or the thermodynamic side?
Kinetic.
Thermodynamic.
NaOT is a weak base.
Oh,
that
yeah,
is
thermodynamics, sorry.
So, do you agree that we'll put OET methyl here? Right?
Yes.
Oh, okay.
What
Oh,
about after 4 and 5?
oh, okay, okay. Yeah,
ETO doesn't.
then you get the
But where?
1,3-BR. Under the methyl? No, not under, like,
Thermodynamic or
Like
kinetic position?
right here?
No, no, OET is a weak base, it gives us thermodynamic enolate only.
Mm-hmm.
So OET, that's why I was really happy to hear that you guys did that first, is that still going to deprotonate at that position?
Yes.
It's sodium ethoxide, sodium
that's what I said.
ethoxide,
I think that was what you were trying to hit on.
bases
yeah.
are going to deprotonate in the thermodynamic position.
Mm-hmm.
And then SN2 will happen on that same position, so what is that going to create?
It'll the dibromocyclopropane.
There's
Comes-
no cyclopropane yet.
No,
There's no cyclopropane.
the propane.
But
The 1,3.
you're right. So at the end of that, we will have 1, 2, 3.
Okay.
That's why,
Mhm.
as Ali said, now let's use LDA, because LDA, this is perfect to deprotonate there. Create a kinetic enolate. When the
Mm-hmm.
kinetic enolate is created, and then SN2 happens,
Mm.
that's where the ring
Close.
gets created. Exactly, that's where the ring gets closed.
Mm.
Does that
Okay.
make
Yes.
sense, everybody?
Mm-hmm.
Please go through the rest also. Please make sure you are able to create a synthesis scheme for each of those. Let's go to the next reaction, and this is called aldol reaction.
I have a quick question.
Yes,
on the
please.
last one.
Yes.
Could you instead, would it be fine to write instead of, NaOT for the first step, do LDA and have it that way?
Sure, absolutely. So are you saying that could we have done,
LDA.
then I would have done LDA, and then what would your electrophile be?
One,
Methyl
two,
or
three, four.
dibromo?
I did methyl and then NaO, and then for my third step,
No.
I did NaOT. Fourth step, I did the, dibromo, propane.
So you're basically just switching the bases, then I'm assuming you did LDA here,
Yeah,
and then you did methyl, and then LDA again, or ethoxide?
ethoxide.
Okay, I see, you're doing ethoxide here, then bringing in that, and then LDA again?
After the dibromo, yeah.
So the rest is the same, yeah, that would be okay, yeah, because it's, it doesn't matter which side the methyl is on, as long as it's on one of those sides, it's the same product. That's right. Yeah, any other questions?
Good. Well, doing LDA first, wouldn't that be on the other side?
Yes, exactly, but ultimately everything will be on the same, it'll be matching, okay. Let's.
But then you can't start with the methyl, right?
Well,
After the
So-
LDA, or
so-
can you?
the way Camilla said,
Mhm.
so if after step 1 and 2, because used LDA, so do you agree that after step 1 and 2 of the new suggestion, methyl would be here,
Yeah.
right?
Oh, yeah.
And then she's doing the same 3 and 4, exactly the same 3 and 4.
Okay.
So now this will go in
Okay,
the thermodynamic position.
Mm.
1, 2, 3, agreed?
Yeah, same,
Uh-huh.
same.
And then 4 and 5, so this goes in the other position, kinetic. So then it will close, so ultimately it will be the same plot, wouldn't matter. Does
Mhm.
that answer your question,
Yes,
Mark?
thank you.
Others? Okay, let's go to aldol reaction. First of all, I wanna ask you, aldol is a combination of two words. Can you tell me which two words?
Aldehyde and alcohol.
Exactly, aldehyde and alcohol. So, aldol reaction is a condensation reaction of two, and I'll tell you what that means, condensation of two aldehydes or ketones. So, if you have one aldehyde or ketone with alpha hydrogens, remember this entire chapter, or both of the chapters that we are working on are taking reactions on the alpha carbon. So if you have an aldehyde or a ketone with alpha hydrogens, it reacts with itself. So two equivalents of those react with each other. Maybe I should do this. Give me a second. I am going to color coordinate so you can see how those pieces come together. Two equivalents react with each other in presence of a base, and it is a reversible process. Sodium hydroxide, that's why it's reversible, because we are using sodium hydroxide, which is a weakish base in this perspective, in such a way that one of these molecules uses its alpha carbon and the other molecule uses its carbonyl carbon and creates a new bond. So the product is as follows, and I'm going to try and color coordinate so you can see how they come together. The piece that uses its alpha carbon creates a bond from the alpha position to the carbonyl carbon of the other. 1, 2. And that becomes an alcohol. The new bond is this one right here, is the new bond. It's between the alpha carbon of one equivalent of the aldehyde and ketone and the carbonyl carbon of the other alcohol, aldehyde or ketone, creating what we call an aldol, because this is a beta hydroxy aldehyde or ketone. There is an alcohol group in the beta position relative to the aldehyde or a ketone, which is called an aldol. Everybody sees that? Let's look at a specific example and then we look at the mechanism of how is this happening and go through it step by step. But let's look at a specific example. So let's take something like, for example, butanol, let's say. So, what would be the first step? Anybody?
Nucleophile attacks electron.
No.
Can't.
Nucleophile electrophile reaction is always slower than acid-base reaction, as we've said, right? Acid-base reaction is always faster than nucleophile electrophile reaction.
Oh.
Is there a possibility of an acid-base reaction?
Yeah.
Yes.
Because you got a base and alpha hydrogens are reasonably acidic. So, and you have a base to deprotonate. So you have to do, if an acid-base reaction is possible, you have to do that first before nucleophile electrophile. So, where is the proton going from? The alpha.
One of the alpha carbons.
Well, there's only one, but you mean the alpha hydrogen.
The
right?
alpha hydrogens. Yeah.
Perfect, exactly. Creating an enolate. That's your first step. Of course, they're all reversible. I'm just too lazy to do that, but they're all reversible steps. The whole reaction is reversible. Now we have a nucleophile. This, as we saw earlier, enolates are nucleophiles. But then where is the electrophile? A nucleophile needs an electrophile to react with. Where is the electrophile? Anybody?
In the
Another equivalent of the
Exactly.
compound.
See, in all of the reactions we've seen before, the nucleophile, once you created the enolate, that's a nucleophile, then we added a separate thing to act as an electrophile. But in the absence of that, when there is no other thing that could act as a new electrophile, maybe another equivalent of the same thing comes in. Because now, as you were saying earlier, Carter, now there is a nucleophile and an electrophile. So the nucleophile will attack the electrophile in exactly the same way it did before. The only difference is that, so there the nucleophile is attacking the electrophilic C double bond. Oh, that's why we need two equivalents. Basically, one molecule is reacting with itself, another equivalent of itself. So the alpha carbon of one is connecting to the carbonyl carbon of the other. You guys see that? So what does that create?
And
1, 2, 3, 4, 1, 2, 3, 4, and O minus. You guys agree?
yep,
Where is the new bond? The new bond is this bond right here, is the new bond. This is how the two pieces came together. And then what? What do you think should happen next?
the oxygen that has the negative charge gets protonated.
From where?
Water.
Right? We created water earlier. Water can protonate and create. So once again, if I were to draw those two pieces and kind of sort of show you how they came together. Sorry, 1, 2, I got an extra carbon in there. And here is our new bond, alpha carbon to the carbonyl carbon of the other. That's the new bond. So it is beta hydroxyaldehyde or ketone is the product. Does that make sense?
Mm-hmm.
Do you see how, am I missing carbons? 1, 2, 3, 4, no. Everybody okay? Am I missing something, Emma? All okay?
I was wondering if the alcohol would survive in a basic environment.
Say that one more time.
If the OH would survive in a basic environment?
What do you mean OH minus OH, which OH?
The OH on the final product.
Alcohol OH?
Yeah.
Are alcohol strong bases or strong acids? No, not at all. So can we deprotonate an alcohol with hydroxide? If you remember when we studied alcohols a few, I don't remember when. But can we deprotonate an alcohol with hydroxide? Not at all. We need a very strong base to deprotonate that, such as hydride or amide or sodium metal or lithium metal. Hydroxide can't deprotonate alcohol, at least not to a substantial level.
So only,
So
I guess the question was like, only with carboxylic, that's when we can,
Because that's a stronger
because
acid.
that's a strong acid.
Exactly.
Okay.
It's all about that equilibrium, right? Acid-base equilibrium. If hydroxide were the base to deprotonate an alcohol, the equilibrium is in direction of the reactants,
Yeah,
not
but
the
here
product.
is not.
Carboxylic acid is different, exactly. So the answer to your question, Emma, is no, it is totally safe because that's not a strong enough base to deprotonate an alcohol. An ordinary alcohol. Now, if this were a phenol, then it's a different alcohol because of their pKa values and all. Does that make sense?
Yeah.
Yeah. So no, in that case, it's totally fine. It's totally okay. Hydroxide is not a strong enough base. Do you guys see how the pieces are coming together? So if I asked you, without writing a mechanism, if I asked you, please tell me what will we get? Without the mechanism. Can you take two of these of course, I didn't say to, but you have to assume that it has to react with itself. Can you tell me what the product would be?
Alpha carbonyl.
NOH.
And no, we can't name it, so don't worry.
Oh, okay.
That will be difficult, because cyclo, how do you do that? So it's okay to just draw it or show it to us. That's totally fine. So how do we take one piece which uses its alpha carbon, connects it to the carbonyl carbon of the other to create a beta hydroxy aldehyde or a ketone, in this case ketone, because it's a ketone. So if I have one of them using its alpha carbon, so creating a bond, right,
With another ring.
with another ring, but the other ring is using its ketone carbon,
It's carbonyl.
so it's becoming an OH.
Yep.
Is this what you all do?
Yep. That's what I
Everybody
got.
okay? Let's quickly write a mechanism. Quickly. So what's the first step?
Base attacks one of the hydrogens.
The base
Um,
takes one of the protons in the alpha position, makes an enolate. Isn't that what you're saying, Carter?
Mm-hmm.
Makes an enolate. Okay, good. Now we have a nucleophile. So what will the nucleophile do?
Attack the electrophilic carbon.
Which is the carbonyl carbon of a different molecule, of another molecule. Agreed?
See?
That is where the bond, the new bond gets created. Everybody okay?
Mm-hmm.
And what would this do?
Accept a proton.
From?
Water.
So this is really a base catalyzed process. If you think about it, the base hydroxide is a catalyst. It's being used first and produced later. Everybody okay? Cool. So if this makes sense, please tell me. Take a few moments. Can I scroll up? Is that okay? Yeah. Carter, do you have a question?
I needed to finish.
He just wanted to finish that. Or
Yeah,
take a picture.
That's why I like board, because there's more space.
Yeah,
This is
there's a
very
lot of
restricted.
space. Yeah.
Very restricted. Okay, so are you good, Carter?
Yep.
Okay. Please tell me, take a few moments, give me the products. Please take a few moments, give me the product. Products. So once again, please keep in mind, two equivalents. One is reacting with another equivalent of itself. One is using the alpha carbon because it's becoming an enolate. The other is using its carbonyl carbon because it's bringing in the electrophile to create that new bond. The product is beta hydroxy aldehyde or a ketone.
Alpha attacks the carbonyl carbon right here. NaOH. Carbonyl.
product will be a beta hydroxy. I think you lost a carbon, or no, you didn't lose carbon, you just. You did lose a carbon. No, that's wrong. It's not wrong. So the alpha carbon is using the CW bond of the second molecule. Where's your alpha carbon? Where's your carbon? Using it the same. Think about that.
Alpha, carbonyl.
It's still alpha hydroxy. The product is beta hydroxy. No, it's not that one. Which carbon is this? And where did that hydrogen go? No, think again, you're going too fast. Try again. Okay.
This is what I got for 15.
Would be this here? Yeah.
Um,
Same one, right? I got it.
This is the carbonyl carbon of another equivalent.
Guys, alpha carbon of one is attaching to the carbonyl carbon of the other.
This is the alpha carbon of the first one. This is the carbonyl of the second
So
one.
this
Okay.
one is using it.
This is the first one and this is
This
the
one is
second.
using
Yeah.
alpha carbon, right? The other one should be using it carbonyl carbon.
Oh, yeah.
I also, if it helps, you can label the carbons, like write a C for carbonyl and an alpha symbol for alpha.
Oh my goodness.
Am I carbon short?
No, you're good. I think you're sure.
Yeah, exactly.
1, 2, 3.
There you go. Now it's, exactly. Does that make sense?
And then the OH here.
No, yeah, exactly, yeah. I'm just looking at the first.
The first and the second.
Here's the first one.
Yes.
Look at.
Is it, yeah, absolutely. So the carbon, alpha carbon of one is connecting to carbonyl carbon of the other. Good.
I
haven't seen
also labeled them.
That's fine. It's up to you
Yep.
how it works out for you. So that's alpha and 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4. Oh yeah. Okay, good. Very cool. And yep, good job.
Can I do it? Yeah. No. So did you do it on that side first? The OH?
I did it from here, and then I just did it so that it would. Imagining that another one of this, since we're bonding with the carbonyl carbon, it would turn turn that one into an alcohol. So that's why I wrote the alcohol at the end, and then just did my 1, 2, 3, 4, 5.
So we're here. So you went up, but you could have gone down too?
Yeah, I could have gone down, but I just decided for maybe a practical purpose, it might to go up. I might go up.
Okay. If not, I'll figure it out. Did you figure it out? Yeah. That's your alpha. So make sure the other is on. All good, everybody? Make sense? Cool. What are the products? Let's write them quickly.
Other products?
So, can I just say pH?
Yeah. Since.
So that's using its carbonyl carbon, that's why it became OH, connecting to the alpha carbon of the other, and
Oh, just one.
is that okay? yours might look different, but is it the same thing? You might have turned it around. Agreed?
Mm-hmm.
Okay, next one.
Another equivalent of the two butanol attacks.
Is that okay? Yeah?
Yep, makes sense.
Okay, next one, so.
No, I didn't. Oh, wait.
Is that okay? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Is that okay? And then the last one. Is that it?
Yeah.
But does everybody understand how the two pieces are coming together? Okay. So this is aldol reaction, which has very limited use. Why the heck did we do this if it isn't? Because of what we can do with it.
Oh.
It itself is actually not very useful. Aldol reaction itself is not a very useful reaction because it's reversible. What it is useful for is that if we heated the aldol reaction product, if we took the aldol reaction product, the beta hydroxy aldehyde ketone product, and heated it, it undergoes dehydration. It loses water molecule and it loses from the alpha beta position the OH in the beta position, and one H from the alpha position basically creates H2O. We'll write a mechanism for that in just a second, and creates the product that is more useful, and that is an alpha beta unsaturated aldehyde or a ketone. Creates a double bond in the alpha beta position. So this whole reaction, starting from the beginning to the dehydrated product, is called aldol condensation. Everybody okay? Yes, the aldol reaction product is created, but then that undergoes dehydration in the alpha beta position to create a conjugated aldehyde or a ketone, which is stable. So let's look at the mechanism for the dehydration step. If we were to write the mechanism for the dehydration step here, what would be the first step? Oops, sorry, I have an extra. The first step is the base
So
taking a proton from an alpha position. Because there is still hydrogens here. Those can be acidic if there is a base.
Mm-hmm.
So the base can actually take that proton, create a carb anion that is resonance stabilized, an enolate, basically an enolate, isn't that right?
Yep.
Now whether I draw it this way, please take a look. Whether I draw it this way as a carb anion or I draw it as its resonance enolate structure, does that matter? Does that matter?
No.
And it's really a preference thing. Which way do we want to write it as? Do we want to write it as a carb anion or the enolate structure, as because they're both resonance hybrids? And remember, resonance hybrids don't exist. What exists is, excuse me, did I just say resonance hybrids don't exist? I've been saying that for a little bit. Sorry, let's scratch that, please. They're both resonance structures, and resonance structures don't exist, hybrid exists. Exactly. So whether, doesn't matter which structure you draw. It really does not matter at all. So the point though is, it is this conjugate base that kicks out a leaving group. Oh, but you said hydroxide is a bad leaving group. Yeah, but in this case, there's already hydroxide present. There's already hydroxide present in the reaction mixture, so kicking out more hydroxide is not going to affect the pH of the system at all, hence no big deal.
Mhm.
So kicks out the hydroxide, takes a proton. This is E1Cb. This mechanism is not E1, it's not E2, it is E1Cb. Basically E1 going through the formation of a anion intermediate. No carbocation, and it's not one step, it is E1Cb because it goes through a conjugate base formation. Now, if you drew the other resonance structure, how would you show it? Same way, you would show those arrows, show this arrow, and kick out the leaving group. So it doesn't matter which structure you prefer to show. The product after OH is kicked out will be an alpha beta unsaturated aldehyde or a ketone. Where are the two pieces? Again, one piece uses its alpha carbon. That's one piece. The other piece uses its carbonyl carbon. That's how they're coming together. Does that make sense, everybody? So, if this reaction is done at higher temperatures, it goes through the reaction, the aldol reaction product and gives us the condensation product. But if you do it at low temperatures, it stops at the first step. So what I mean is, basically, here's an example. Is it okay for me to scroll up, everybody? Okay, so what I mean is, by the way, the notes are already on Canvas. If you remember, I told you it first at the start of this quarter. All the chapter notes are already posted on Canvas. So for example, if I take cyclohexanone and I do this reaction either with NaOH at 0 degrees Celsius, or maybe 10, or I do it at 100 degrees Celsius, so I'm refluxing it, I'm cooking it really. The outcome will be slightly different because this is low temperature, so this reaction will predominantly create the beta hydroxy ketone, but the other one, which is at higher temperature, will go an extra step and give us the alpha beta unsaturated, because, and you can even keep that and get the same outcome. So it really depends on what we want to do. Aldol condensation is the more useful path than the aldol reaction. Meaning losing water is actually going to create a better outcome in terms of the yields of the product than the reaction itself, because that's more equilibrium. So, does that make sense, everybody? Okay, let's try this a few times then. We will also write mechanisms. So what will this create? What would you expect it to be? Condensation or not condensation?
Condensation.
Condensation, why do you say condensation?
Heat.
Because there's heat, exactly. Which means that it will definitely make, let me draw it first, the aldol reaction product, absolutely it will, but because there is heat, this won't survive. This will go an additional step, lose the water from the alpha beta position and give us the condensation product. So this is one piece that is creating a bond, a double bond in the alpha beta position, and here is the other piece, methyl and a T. That's it, right? 1, 2, 3, 4, 1, 2, 3. That's how they're coming together. The point, the point of connection between the two parts is still the same. alpha carbon of one and the carbonyl carbon of the other. That's where they're coming together to create a new bond. Let's write a mechanism to explain every step of how this whole reaction is taking place. So what would step number 1 be? Anybody?
Okay. Base attacks an alpha hydrogen.
And notice there's only one side where that can happen from, because the other side does not have hydrogens on the alpha position. So only one enolate is possible to be created, okay? So that makes an enolate. Then what? The enolate acts as a nucleophile.
And
Attacks.
attacks the
Uh-huh.
carbonyl carbon of one of its own.
So, okay. What next? What next, guys?
The oxygen gets protonated.
The O minus gets protonated from water, recreates hydroxide, okay? Makes the aldol reaction product. This is the aldol reaction product.
Okay.
What next?
Take the water.
How? But you gotta show step by step.
Oh.
How?
How,
Oh,
go Mar, go.
to know you.
Okay. So,
Yeah, go ahead.
so, a hydrogen,
How about the base takes another alpha proton?
the base takes
The
another
base
alpha
Creates
proton.
the enolate again. And
Okay.
as I was saying earlier, it doesn't matter which structure of the enolate you show, because they are resonance structures, but the point is make the enolate again. And then what? Then this pushes out the leaving group. This is E1CB. Put it on here. Give you a little there. This is E1CB. So that's the whole mechanism from the front, from the reactants to the final product. Everybody okay?
Okay.
Okay, let's do it again. If this makes sense, please tell me what is the product.
Can I take a picture of the previous one?
Guys, then let's do it faster, please, because we are, as it is, slowed down.
Okay.
And as I said, these notes are all on Canvas. The notes are already attached on Canvas, I'm just following them,
Okay. Thank you.
okay? Let's, how about this one? What's the product?
The conjugated ketone.
So after the dehydration, that's what you mean, Carter?
Yes.
Good, okay, so what would that look like? Let's write it, let's try and draw it. So, here is the first equivalent, ketone, and then it is going to create a double bond where the ketone was. Do you agree?
Yes.
Yes? Can you all write the mechanism? Everybody good? Can I get I got one shake of a nod of the head. How about others? Can you guys write the mechanism at home? I got another one. I got third. Perfect. Please do. Please practice the mechanism from the front to the end. But does everyone understand how this product is being created though? So then, were you gonna say something, Jane? No. Oh. So then, if that is the case, can you tell me, when we go backwards? Can you tell me what was being used to create this alpha beta unsaturated ketone? Or using sodium hydroxide is the base that's used, or could we go in the reverse direction and you tell me what was used to create each of these products? Go ahead. And you feel free to draw it on the screen if you would like to that. Not asking for the mechanism, just asking for the reactant to create each of these. So we're going backwards. Very good.
Okay.
That's a double bond, right? That's the CO is a double bond?
Yeah.
Okay, good. No, absolutely right. Very good. Cool.
Anyone else?
They'll come.
Does anyone agree with what I wrote?
Yeah.
Okay.
Is everybody following? Does that make sense? Yes? Vincent? Kind of? Did he say
I mean-
kind of?
I'm slow, but
No, that's
I'll
fine.
get there eventually.
Oh, is that a double bond, Carter?
Oh, yeah, I was intending to write a double bond there.
No, I mean the carbon-carbon double bond at the bottom.
Oh, no.
There's a erase thing, one of the buttons on the top is an eraser.
Yeah,
See it?
yeah, I see it.
So it's the double bond where the two pieces came together. You see it? Do you all agree? Everybody agrees? Yeah? Is that it?
I agree with what I wrote. I don't know if anyone else does.
Okay, so what you're taking out is the double bond, right?
Exactly.
Okay,
That's the most important hint is that double bond.
okay.
Because that alpha beta position is where the two pieces came together. Exactly. So if you break the molecule apart in that position, that gives you the two pieces. Now guys, remember, we ultimately took out water. Remember that we took out H2O. So if you're thinking in the reverse direction, the two hydrogens of H2O went there and the oxygen of H2O went there. That's why you have that as the product. I mean, as a reactant. Does that make sense? Everybody's okay?
Yeah.
Questions?
They're all NOH, because I see an H there, but. is
No,
that-
in the if you write the overall equation, isn't the overall equation
heat.
making water?
Yeah.
Yeah.
So we're thinking backwards, if you were to add the water back, going reverse direction.
Oh, that's right.
So that's how
So then,
two hydrogens from the alpha carbon
Oh,
and
yeah.
oxygen from the carbonyl carbon.
but that would be going back. Yeah.
Yeah,
Mhm.
to think reverse, I mean, it's just a hint to be able to figure out. Does that make sense, everybody?
So those on
Yes.
there are all with heat added?
Yes, assume, yes, assume.
Without heat, it wouldn't do the condensation.
Typically, condensation will be hard to do, yes. But condensation is the desired product, so why would so the point is, typically when you would do aldol, you would do reflux, so that you can go all the way. So that is aldol reaction and aldol condensation. If everybody understand aldol, can you please tell me how many products, aldol, obviously I'm talking about condensation, aldol condensation products would I get if I were reacting acetaldehyde with acetone? So two different, so far, it's been the same molecule reacting with another of its own self, right? It's been basically two of the same substances, molecules reacting with each other. What if we had two different aldehydes or ketones in the system? How many products can I get?
Free products? Not free. Okay.
I see why you said three though, but not three. Think a bit deeper.
Mm-hmm.
How many products possible? How about four?
That was
Four
what I was
products.
gonna say. That was what I was gonna say.
So
Four
how?
products.
Can this make an enolate? Can this make an enolate?
Yes.
Does it have an alpha hydrogen?
It could.
Is that a yes? Let's
Yes.
Yes,
practice
yes.
this, guys. I'm only hearing from 2 or 3 people today.
So just alpha.
Yes? So product number 1, this makes an enolate and reacts with itself. Agreed?
Mm-hmm.
Product number 2, can this make an enolate?
Yes.
So this makes an enolate, reacts with itself. Agreed?
Yes.
Yes.
Product number 3, this makes the enolate and then reacts with this guy.
Oh.
Mm-hmm.
Product number 4,
That.
this makes the enolate and reacts with this guy. You guys see that? Please take a couple of minutes, draw all 4 for me. 4 products. 30 seconds for each. That's 2 minutes.
I get double.
No.
No, Mar.
I'm
No.
just kidding. So let's draw those three. So 4 possible products. Sorry, Camilla, I walked away from the station here. 4 possible. Oh, good. 4 possible products. If can I just call them A and B so that we can just say A. If A is the enolate, meaning it's using its alpha carbon and reacting with another equivalent of itself, do you agree? Agree? This
Yeah.
is AA. If A is the enolate, A is the electrophile. Agreed?
Oh.
If B creates the enolate, uses its alpha carbon and reacts with another equivalent of itself, so this is BB. Agreed?
Okay.
Now, what if A makes the enolate but reacts with an equivalent of B? Do you agree?
Yes.
But then what if B makes the enolate and reacts with an equivalent of A? They're all different compounds. They're all structural isomers if you think about it. Isn't that right?
Yep.
4 possible products. This kind of reaction where we are doing aldol condensation but using two different aldehydes or ketones is called crossed aldol. Cross basically meaning that we are using two different substrates. But who wants to deal with a reaction with four products and then all four are equally likely? Who wants to deal with a reaction that you have four different products in there? Now you have to figure out how do I separate all four of them. That's a mess. So crossed aldol reactions are done only with only one substrate or one reactant that can make an enolate and the other cannot. Otherwise, there'll be so many different products that we then have to figure out how to separate them from each other. That means also my yield is low, my productivity is low, efficiency is low. That's not a good situation to be in. So we do crossed aldol in such a way that we choose our reactants such that only one can make the enolate and the other cannot. What does that mean? The other cannot. How do I say this? What should there be, or sorry, let me say that again. What structural feature will be needed for any aldehyde or ketone to not be able to make an enolate?
What would be the
Subs-
acetone? No.
So what does that mean, third butyl on both sides? I mean, it doesn't have to be third butyl. So what must be the case so that you cannot create an enolate?
No
Which hydrogens?
no alpha hydrogens.
Exactly.
Oh.
No alpha hydrogens. If there are no alpha hydrogens, then you can't make an enolate, because in order to make an enolate, you have to deprotonate at the alpha position. So crossed aldol reaction is really useful when only one reactant has alpha hydrogens. It can become an enolate while the other cannot. So for example, can this make an enolate? Can benzaldehyde make an enolate?
No.
How about this? Can this make an enolate?
No.
How about formaldehyde? Can that make an enolate?
No.
So the point is, this is just some examples that they don't have any alpha hydrogens, so they cannot make an enolate. Does that make sense, everybody? There are
Yeah.
others too. I'm just choosing a few examples to show you, that's all. So crossed aldol reaction works in two situations. There are two ways in which crossed aldol reactions can be made to work. One of those situations is by very strategically choosing one of the carbonyl molecules can create an enolate while the other cannot. Can someone tell me what would be the product here?
Two butanals.
Then why do we have formaldehyde? We're talking crossed aldol right now.
Okay.
There are two different reactants, so you have to think about they're both reacting with each other.
Okay.
Can the first one make an enolate?
Yes.
The first one, please look carefully.
Oh no.
The
Formaldehyde
first one has
cannot.
no alpha hydrogens, so it cannot make an enolate. Can the second one make an enolate?
Yes.
So you got to picture this. If this becomes an enolate, which means it's going to use its alpha carbon. This is the one that's going to use its alpha carbon. I'm not writing the mechanism, I'm just walking through my thought process. And if this aldehyde butanal is going to use its alpha carbon, then what's the role for formaldehyde? What's the role for methanol?
It'll create a primary alcohol.
It will be the electrophile,
Mhm.
right?
Yeah, it
The
will be an
nucleophile to
electrophile.
attack and create and react with the electrophile. So and we're thinking condensation, guys. So what will be the final product? Do you agree?
Yes.
Agree? Yes? Everybody? Please make sure you can write the whole mechanism from the start to the end. But does everybody agree? Once again, the piece that cannot create an enolate acts as the electrophile, and the piece that can create an enolate uses its alpha carbon. Does that make sense, everybody?
Yes.
Okay, so please then tell me, what would the products be? So if that makes sense, please go ahead, tell me for the first two, what's the product, for the second two, what reactants will be needed to make those work. It's exactly the same reaction as aldol condensation that we saw. The difference is there are two different reactants. One that can make the enolate, the other that cannot make the enolate. So the one that can make the enolate uses its alpha carbon. The one that cannot make the enolate uses its carbonyl carbon. carbons. One whole benzene ring is gone. Where is that going? I don't know. Where are you going?
I don't know what I'm doing, but let's try it.
Here.
Let's see if I got it.
Okay, cool, that's fine. But the minor focus is the cross.
Oh,
Yes.
right. Oh,
You
that's not-
added,
almost there, huh? Just, yeah.
you, I
think I
believe you
got it.
added an extra carbon here because there's no carbon on this.
Oh, where did I get that?
There's a,
Oh, I got this one here.
oh,
But no, I shouldn't have. Yeah, I got confused with the other one. Yeah, you're right.
yeah.
Oh, down, okay.
Oh, I was trying to put these and these together, but no, just reacted it with this
Good.
same one, right?
Mm-hmm.
Everything okay? Yeah.
Now
You
it's
write
good?
some answers up on-
Yeah, yeah.
Write some answers on the screen. Got it? Think so. Why think so? Let's make it even funner then. Oh, come on. Being able to visualize others. Yeah, I get it.
So,
Yes.
do we just get one then?
Yeah.
one?
We're looking at the crossed product only. So you're right. That came in from here because it can make an enolate, whereas this piece is here because it can't make an enolate. Yeah,
Oh,
good.
okay.
I mean, you drew this,
Yeah.
correct? No, you're
Yeah,
right.
I had put here a method, but no, that,
There's no method.
I was thinking
Yeah.
that one, but no.
No, we're not talking about the symmetrical product. We are thinking about the crossed product.
Okay.
Yeah.
Okay. Everything okay here? Okay. Does anybody else wanna go put up the answers?
Any
Otherwise Carter has the,
Any other takers? Otherwise,
Okay.
I'd be like that.
No.
let's go ahead. Let's finish it quickly, Carter.
Okay.
I think I. Did I get it? No. I put an extra card. Won't there be?
No,
No?
oh no, I was telling, sorry, no, I was speaking to Carter.
Oh, okay.
I didn't even, what were you saying? I'm speaking to Carter. Sorry, Carter,
I'm like,
not quite.
okay.
No, the last one.
For the last.
Yeah, what were you saying, Mark?
No, no, I was just,
So once again, the new bond is the double one, right?
yeah.
So this part is using its C double bond O,
Mm-hmm.
and this one is using its alpha carbon.
Okay, yeah. I was inserting an extra carbon there, so, for some
Where?
reason. Right there, like,
I think that's a plus sign.
no, I was, yeah, right here, just because I
No.
thought, you know.
Yeah, so simply just cut it right there. Right there, cut it right here.
Mm-hmm.
That's alpha. So H2 goes here, O goes there.
Okay.
And that's it, done.
The- Where's the H?
Okay, how about I do that?
Okay.
So same thing, just leave it there, thank you. Same thing, cut at the double bond. this is where the molecule came together, right? The
Yeah.
one that's using the alpha carbon has the two hydrogens and the other was the original carbonyl carbon. So that's it, nothing else
That's fine.
changes. So this is benzaldehyde again, because it could not make an enolate. And that is. Sounds okay, everybody?
Oh, yeah.
Is that okay, everyone? Cool, so that's one way in which we can do crossed aldol without getting numerous products, and then you have to figure out how to purify them, how to separate them from each other. This is one way of achieving it. Another way of achieving crossed aldol is called directed aldol. So this is also crossed aldol. But here's another strategy of being able to successfully achieve crossed aldol condensation, and that is to use a strong base. See, if you've noticed, all of these reactions, our base has been sodium hydroxide, which is a weak base, right? With sodium hydroxide, when the enolate is being produced, you'll have equilibrium reaction because that's a weak base. But if we used a strong base, so for example, we actually strategically do the reaction where we use LDA first as step number one, which causes all the molecules, because it's not an equilibrium process, all we have is the enolate, we don't have anything else, and then add the other reactant, whatever that might be. So then this is more strategically done to create a very specific 1, 2, 3, 1, 2, 3, 5. So this is called directed aldol. It's done in a very directed manner by choosing a strong base in the first step, then as a separate step, bring in the other electrophile to carry out the reaction. So for example, I'll give you one more example of a directed crossed aldol. So let's say we start out with step number 1, LDA. It's a very strong base, so the deprotonation step is not a reversible step, or rather I should say the equilibrium of the deprotonation step is in the direction of the products. So it's great. We have only the enolate at that point in time, and then the enolate, once you've got all the enolate as a separate reaction, we can introduce the other compound. So what will this produce? The enolate comes from the first one only,
Okay.
makes the enolate. The second one is only using its carbonyl carbon. Get that as the product. So it's more directed, it's more strategic in its approach. Everybody okay? Questions? So crossed aldol can also be done in this way by using LDA instead of a weak base such as sodium hydroxide. Okay, if that makes sense, here are a few more for you to try at home. Is again just to give me the reactants. These are crossed aldol products. Just give me the reactants. Again, practice please. By the way, is this aldol? Do you guys recognize this as aldol?
Yes.
Because it's not a condensation product, it is the
Aldol
reaction
product.
Exactly. Same concept though. right? So please work through these to make sure that you are able to identify how the two pieces are coming together. Everybody okay? Questions? I did have one question for you. If you understand the aldol condensation reaction, can I scroll up? Is that okay?
I'll give you one second. I'm almost there. Okay, for me.
Okay. Can you please tell me, I'll just make it smaller so hopefully I can fit more. What will be the final product? What will be the final product? You're smiling. I think you see it.
Mm-hmm. I'm gonna go with this.
What? What?
I
You're
don't know.
laughing, so I'm wondering why. Do you see it? Ha 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 ha. Ali, you don't feel. Carbon can never make 5 bonds. And that's the point here. So what will be the product? Exactly. It can't go. The point is, guys, how many alpha hydrogens does it have?
It only has one.
So, if it has only one hydrogen at the alpha position, how many hydrogens can be deprotonated from the alpha position?
One.
Only one, because there's only one.
Mhm.
So, can it do dehydration?
No.
Can't.
Oh.
So, what's the final? Where will it stop then? Whether you
Aldol.
heat it, it's
Aldol.
at the reaction, aldol reaction stage, and not the aldol condensation stage, because no matter how much you're heating it, it cannot do the dehydration part. So it has to stop. Does that make sense, everybody? 1, 2, 3. 1, 2, 3. Does that make sense, everybody?
Mm-hmm.
There is no hydrogen, no more hydrogens in the alpha position, no more. So therefore, it cannot do the dehydration step. Otherwise, we'll end up making 5 bonds to carbon, in which we all know there's no way carbon can ever make 5 bonds. Not possible. Does that make sense?
Mm-hmm.
Everybody okay?
Mm-hmm.
So let's make it a bit funner. We have 2 minutes. Let's at least end with a bang. Yes, of course.
Fun.
And that is intramolecular alcohol. What does that mean, intramolecular?
Within the molecule.
And please remember, when intramolecular reactions happen, what would that create? It would, if it reacts within itself, what would that end up doing?
A cyclone.
Create a ring. And what size ring are favorable?
5 to 6 members.
5 or 6 membered rings are favored, the others are not favored. So, for example, what would that make?
A cyclohexanone.
carbon, the other uses its carbonyl carbon. So from where to where? Okay, it's symmetrical. I chose it to be symmetrical on purpose.
Mm-hmm.
Can this alpha position lose a proton? I'm calling it 1. Can it lose a proton?
Yes.
Okay, but then it's going to cyclize with the other ketone. That's a 3-membered ring. Is that favorable?
No.
No. So that's not the direction we want to go to. Okay. Can this alpha carbon create an enolate? Can it lose a
Yes.
proton?
Yes, it can lose a
Okay, and then
proton.
it will react with the other C double bond O. So what size ring is that?
5.
5.
Oh.
5. Is 5 okay? Yeah, 5 is okay. 6 is not possible in this example. In this example, you can't get a 6. So what's the product?
Oh.
The product is going to be,
5.
but then
With a double O.
where? Double, okay,
Well,
yeah,
not CO.
and what else between 1 and 5?
A
So-
double bond.
Exactly, because you're doing condensation. If this is carbon 1, that's carbon 2, this is 3, this is 4, this is 5. So there is a double bond between carbons 1 and 5. What am I missing? I'm missing something.
The methyl.
Methyl
The methyl group.
on the carbon 5. This is where the molecule came together. Right there. You guys see that?
Yep.
This is intramolecular aldol, and I know I'm out of time, so can I just, well, I've given you a few things to work on between, so I guess we'll stop here, we'll do the rest on Wednesday. Yeah. For the exam tomorrow, let's meet here. If this room is busy, then we'll go to 105, which is across the hall over there. Is that okay, everyone? What's this?
And it'll be over chapters 19 to 21.
I don't know the numbers, let's see, 19, 20, and 21, yeah.
Okay.
Second half of 19, because we covered some of it for exam.
Okay.
But still, it's cumulative, right? Anyway.
Okay, thanks.
Yes. Oh, yes,
I noted
it's an
what the
extra
exam
credit
will
I'm
be
giving
on.
out to everybody.
You what?